A singly linked list is a linear collection of elements called nodes where each node stores two pieces of information. Data dash the actual value, e.g. an integer, a string, a complex object. Next pointer dash a reference address to the node that follows it in the list. The list is accessed through a single external reference called head. The head points to the first node. The last node's next pointer is null or none, signaling the end of the list. Struct node open brace data :t semicolon, any type t next node star semicolon. Address of the next node null, if none close brace node star head equals nullter empty list. Pointer layout analogy: imagine a chain of people standing in a line, each holding a rope that points to the next person. The first person head is the only one you can see from outside. Everyone else is reachable only by following the ropes. The list can be visualized as head arrow data pipe next arrow data pipe next arrow dot 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 arrow data pipe null. The simplicity of having only one pointer per node makes insertion and deletion cheap at the ends, but locating an interior element requires walking from the head, which gives n search time. Mathematical view: if the list contains n nodes, the total memory used is n times size of data plus size of pointer. The height of the structure is linear (n) because each node adds one level of indirection. Insertion at the beginning. The operation adds a new node before the current head, making it the new first element. Allocate a new node, new nodes. Set new node data to the value to insert. Point new node next to the current head. Update head to new nodes. Function insert at front head reference value :. New node gets allocate nodes. New node dot data gets value. New node dot next gets dereferenced head reference, current first node may be null. Dereferenced head reference gets new node head, now points to new node. Return dereferenced head reference. Time complexity: the algorithm performs a constant amount of work regardless of list size, allocating one node and updating two pointers O1. Space complexity: only the new node is allocated O1 auxiliary space, excluding the memory required for the node itself, which is O1 per insertion. Real-world analogy: think of a queue at a ticket counter where the clerk can decide to let a VIP cut in line. The VIP just steps in front of the first person, no one else needs to move. Edge cases. Empty list head is null. Step 3 sets new node next to null, which is correct. Very large list, still O1 because no traversal is needed. Insertion at the end. Two common designs exist. One without a tail pointer, only head is kept. Two with a tail pointer, an extra global reference tail always points to the last node. Without tail, steps: allocate new node and set its data. Set new node points to next to null, it will become the last node. If head is null, make head point to new node, list was empty. Otherwise, start from head and walk until a node cur whose next is null. Set cur points to next to new node. Define function insert at end with head reference and value. Allocate new node, set new node data to value, set new node next to null. If dereferenced head reference equals null, then set dereferenced head reference to new node and return. Set cur to dereferenced head reference. While cur next not equal to null, do set cur to cur next. After the loop, set cur next to new node. Complexity: traversal touches every node, which is O of n time. Only one new node, which is O of 1 extra space. With a tail pointer. Steps: allocate new node, set data, set new node points to next equals null. If head is null, set both head and tail to new node. Else set tail points to next equals new node and update tail to new node. Define function insert at end with tail with head reference, tail reference, and value. Allocate new node. Set new node data to value. Set new node next to null. If dereferenced head reference equals null, then set dereferenced head reference to new node and set dereferenced tail reference to new node. Otherwise, set dereferenced tail reference points to next equals new node and set dereferenced tail reference to new node. Complexity: no traversal, constant work, which is O of 1 time. Same O of 1 auxiliary space. Analogy: picture a train that you can add a new carriage at the back. If you know where the last carriage is, tail, you just hook the new one directly. If you only know the front head, you must walk through each carriage to reach the rear. When to keep a tail. Frequent end insertions keep tail for O of 1. Memory overhead is negligible, just one extra pointer. Insertion at the kth position. 0 less than or equal to k less than or equal to nk equals 0 means front. K equals n means append. General procedure. Validate that k lies in 0 to n. If not, report an error. Allocate new node and store the value. Special case k equals 0, reuse the insert at front routine. Otherwise, walk from head for k-1 steps to reach the node previous that will precede the new node. Set new node next equals previous next, might be null if inserting at the end. Set previous next equals new node. If a tail pointer exists and k equals n, update tail equals new node. Complexity analysis. The loop walks k-1 nodes, so O of k time. In worst case k equals n, O of n time, only constant extra storage O of 1 space. Empty list, only k equals 0 is legal. The algorithm behaves like front insertion. Insert at end, k equals n. After step 5 previous next is null, we must update tail if present. K out of bounds, handled by validation. Real-world analogy. Think of a bookshelf where you want to place a new book at position k. You count from the left head until you stand right before the spot previous, then slide the new book in. If you want it at the very left, you just put it in front. If at the far right, you walk the whole shelf. Deletion of the first node. Removing the node that head points to. Methodology. 1. Ensure the list is not empty, head not equal null. 2. Keep a temporary pointer temp equals head to remember the node to free. 3. Update head equals head next. The second node becomes the new first, may be null. 4. If a tail pointer exists and the list now becomes empty, head equal null, set tail equal null. 5. Deallocate temp free memory. A complexity. Direct pointer updates, no traversal leads to O1 time. No additional auxiliary storage leads to O1 space. Analogy, imagine a line of customers at a bank. The teller serves the first person and that person leaves the line. The next person instantly becomes the first without anyone else moving. Special cases. Single element list. After step 3, head becomes null. We must also reset tail to keep the structure consistent. Memory safety. In languages without automatic garbage collection, C/C++, forgetting to free leads to leaks. Deletion of the last node. Because a singly linked list does not have a backward pointer, we must locate the node just before the last one. Strategies. 1. Without a tail pointer, we still need a traversal from head. 2. With a tail pointer, we still need the predecessor because tail alone cannot give us the previous node. Common steps. 1. If the list is empty, error. 2. If the list has only one node, head arrow next equals null. Free that node, set both head and tail to null. 3. Otherwise, start prev equals head and walk, while prev arrow next not equal to null. When the loop ends, prev arrow next is the last node. 4. Store last equals prev arrow next. 5. Set prev arrow next equals null. 6. Update tail equals prev if a tail pointer exists. 7. Free last. Pseudocode. Define function delete last with parameters head reference and tail reference. If star head reference equals null, then error list empty. If star head reference dot next equals null, then only one node, free star head reference. Set star head reference to null. Set star tail reference to null, return. Set prev to star head reference. While prev dot next not equal to null, do set prev to prev dot next. Now prev dot next is the last node. Free prev dot next, set prev dot next to null, set star tail reference to prev. A complexity. Traversal touches n-1 nodes, O of n time. Constant extra storage, O of 1 space. Why not O of 1 with the tails? Even though we know the last node, we still need its predecessor to set next to null. Without a backward link, we cannot obtain it directly, hence the linear walk. Analogy, think of a train that can only see forward. To detach the last carriage, you must walk from the engine to the carriage just before the last, then uncouple the rear one. Deletion of the kth node. 0 less than or equal to k less than n, remove the node positioned at index k, 0 based. Validate k 0 less than or equal to k less than length, if invalid, error. Special case k equals 0, call delete front. Otherwise, walk from head to the node previous that is just before the target, that is k-1 steps. Let target equal previous arrow next. Set previous arrow next equals target arrow next, bypassing target. If target arrow next equals null, deleting the last node, update tail equals previous. Free target. Function delete at position head reference, comma tail reference, comma k colon, if k less than 0 or k greater than or equal to length of head reference. Then error quote invalid position quote if k equals 0, then delete front head reference, comma tail reference, return prev assign head reference for I from 1 to k-1 do prev assign prev.next now prev. Is k-1 th node target assigned prev.next assign target.next if target. .next equals null removed last node tail reference assigned prev free target. Complexity, traversal of k nodes, O of k time, worst case O of n when k is near the end. No extra structures, O of 1 auxiliary space. Special cases, k equals 0 front deletion O of 1. K equals n-1 last deletion still requires traversal to n-2 O of n and tail update. Single node list k can only be 0, after deletion both head and tail become null. Real-world analogy, removing a specific book from a shelf, you count to the spot before the book, pull the book out, and slide the next book left to fill the gap. If you remove the first or last book, the actions are simpler. Memory management in singly linked lists. Allocation. When inserting, a new node is created using malloc or new in C or C++, new in Java heap allocation, or simply by instantiating an object in languages with automatic allocation such as Python or JavaScript. The size allocated equals size of node equals size of data plus size of pointer. Deallocation. In manual memory languages C and C++, after removing a node you must free node or delete node to return the memory to the system. In garbage-collected languages Java, C#, Python, Go, the node becomes unreachable after pointer updates. The runtime's collector eventually reclaims it. Garbage collection considerations. Reference cycles are impossible in a pure singly linked list because each node points only forward, so traditional garbage collection works effortlessly. However, if nodes hold references to external resources such as files or sockets, you must still explicitly close them before the node becomes unreachable. Forgetting to free memory leak programs memory grows. Fix, call free or delete right after detaching the node. Using freed memory, segmentation fault undefined behavior. Fix, after free never do reference that pointer, set it to null. Double free crash or abort. Fix, ensure each node is freed exactly once. Practical tips. 1. Encapsulate allocation and deallocation in helper functions create node, destroy node. 2. In C++ prefer smart pointers unique pointer to get automatic reclamation. 3. In Java Python rely on garbage collection but still null out large references if you want deterministic release of large auxiliary objects. Mathematical expression for total memory after M insertions and D deletions with no leaks. M total equals open parenthesis M minus D close parenthesis times open parenthesis size of data plus size of pointer close parenthesis. If M minus D equals N current length, then memory usage is linear in N, theta of N. Write the code to insert a node at position K in a singly linked list. Expected answer includes validation traversal loop pointer updates and optional tail handling. Trace the following sequence on an initially empty list. Insert 10 at front. Insert 20 at end no tail. Insert 15 at position 1. Delete node at position 2. Show the list after each operation. Marks are given for correct pointer changes and final layout. Prove the time complexity of inserting at the end with and without a tail pointer. Students must argue that without a tail the algorithm traverses n nodes. T of n equals C times n plus D implies theta of n. With a tail only constant work implies theta of 1. Compare singly versus doubly linked list for deleting the last node. Provide a table. Structure needed pointers steps time space overhead. Singly head optional tail walk to predecessor update big O of n1 pointer per node. Doubly head and tail and previous next use tail dot previous adjust 2 links big O of 1-2 pointers per node. Explain memory management in C for deletion of a node at position K. Must mention free after relinking and show what happens if free is omitted. Design a function reverse list node star head and discuss its effect on insertion deletion complexities. The answer should show big O of n reversal, and note that after reversal the cost of end insert changes if the list had a tail. Scoring tips for students. Write clear pseudocode with proper variable names. Show edge case handling empty list single element. Use comments to indicate why each pointer is updated. For proof questions, start from elementary operations, count them, and use big O notation. When comparing, mention both time and space overhead. Insert at front, add new node before current head, big O of 1 same, big O of 1 no traversal needed. Tail unchanged unless list was empty. Insert at end, append after last node, big O of 1 direct access via tail, big O of n must walk from head. Tail pointer provides constant time append. Insert at position k, 0 less than or equal to k less than or equal to n. Place node at index k, big O of k still need to walk to k minus 1, big O of k same cost. Tail helps only when k equals. Delete front, remove node pointed by head, big O of 1, big O of 1, update head. If list becomes empty, also set tail to null. Delete end, remove last node, big O of n must find predecessor. Big O of n. Even with tail, we need to search for the node before tail because singly list lacks backward link. Delete at position k, 0 less than or equal to k less than n. Remove node at index k, big O of k, same traversal cost. Tail update required when k equals n minus 1. The only operation that benefits asymptotically from a tail pointer is insert at end. All deletions remain linear in the worst case, because we must locate the predecessor of the node to be removed. Space overhead of maintaining a tail is just one extra pointer, big O of 1. For applications with many end insertions, for example building a queue, keeping a tail is highly recommended.